Welcome to Module 9 of BART's Safety Management System Training Program.
This course will focus on change management.
Change management integrate into the foundations of safety management systems.
Change management activities would specifically fall into two of the four SMS components, which are safety risk management and safety assurance. Change management is a process to ensure that all documentation that describes a system and its various components is current and reflects the actual functional and physical characteristics of the system throughout its life cycle.
Requirements.
BART must establish a process for identifying and assessing changes that may introduce new hazards or impact the transit agency's safety performance.
If it is determined that the change may impact its safety performance, then the change must be evaluated through its safety risk management process.
Thinking exercise.
What are some reasons why BART would need to manage change?
For instance, what types of unsafe situations could be created by not correctly tracking changes made within the BART system?
Any ideas?
BART is using a new design for its train wheels in the hope of quieting the ride.
Here is a video on the new BART wheel profile.
Your commute is about to get a lot more peaceful.
Today, BART to quiet those screeching wheels. KPIX5 reporter Wilson Walker shows us.
I live 6-7 blocks from here, and you can hear the screech.
So what's all that grinding and screeching you hear as whizzing by? Well, you've heard the phrase where the rubber meets the road, right? Out where the wheel meets the rail.
There's 2 points that the wheel contacting the rail, and ideally there should only be one.
For all these years, BART's design has presented a problem, those 2 points of contact, which cause the wheel to skip and rattle their way across the Bay Area.
Especially in curved rail, sometimes the current wheels will actually spin.
Then the problem gets worse. That spinning and rattling wears down the tracks.
That rail wear over turns into what looks like a corrugated roof.
And when the rattling wheels hit the corrugated rails,
that's what causes the loud screeching that is so custom to BART right now.
So here's the fix. The wheels will be resurfaced to have a slightly tapered angle, eliminating the 2 points of contact and allowing them to roll more smoothly. Then there's the double payoff of less wear on the rails, meaning BART won't have to spend as much time grinding away all the corrugation that amplifies all the noise. It's kind of a win-win-win.
That is correct.
Saves money?
Yes.
Saves noise?
Yes.
Saves wear on the rails?
Yes.
Now the only problem is that every axle in the fleet will have to roll through the wheel press.
If we did the entire fleet, 669 cars, that's 21,408 wheels that would have to be cut.
Early testing suggests the volume will go down, maybe as much as 50%. So once the new wheels are rolling, BART may never sound quite the same.
We have found a way that it's going to prevent the loud screech that everyone knows.
In Hayward, Wilson.
Why should BART manage change?
Because of the following:
Improved safety,
new materials,
new equipment facilities,
expansion of services,
improved performance,
increased reliability,
better maintainability,
financial considerations,
new codes, standards, or regulations.
Controlling system modification.
Reasons for implementing a systems modification process.
To avoid introducing new hazards.
To ensure incorporation of system changes to reflect modifications.
To ensure internal and external coordination of system modifications regulations.
Here is a change management scenario.
The hexagon-headed bolt used on some wayside equipment is no longer available.
Maintenance replaces the hexagon-headed bolt with square-headed bolt of same size and strength.
Considering the bolt scenario, is this a modification that needs to be monitored and undergo hazard analysis and safety risk evaluation?
Could changing the bolt produce a hazard even though the bolt is the same size and strength? If the hexagon-headed bolt used is associated with a train control system, trip arm, then the change of the bolt head will require configuration management and would require recertification of the modified system through hazard analysis and safety certification.
Summary.
The 1995 Russell Hill subway accident was a deadly train crash that occurred in Toronto, Ontario, Canada. Line 1 Yonge University of the Toronto subway on August 11, 1995.
3 people were killed and 30 were taken to hospital with injuries when one train rear-ended another train.
The subway line was shut down for 5 days following the incident.
Investigations found that human error and a design flaw in the mechanical safety devices caused this accident.
It remains the deadliest accident in rapid transit system in Canadian history.
Slicing through the transit arteries of the major cities in the world runs another type of rail system. It's called a subway. The Toronto Transit Commission, or TTC, has one of the most modern transportation systems in the world. Its subways and commuter trains had never had a fatal accident in its 42-year history until August 12, 1995. 6:02 p.m., the end of a workday. It's the second day on the job for the rookie driver of Run 35. He pulls out of St. Clair West Station and heads underground south to DuPont Station. Suddenly, a stopped train appears directly in front of Run 35. There is nothing the driver can do. Within minutes of the crash, rescue crews arrived at the scene.
Seeing 2 of these large subway cars sort of mangled together, there's really no way to describe it. You have to see it. You know, it's a very large, very strong structure that has tangled itself together, and it's not easy to get it apart.
When you got right to the site, you were met with this catastrophic damage to these trains, this large ball of steel with patients trapped in it.
Many of the victims were freed quickly and transported to hospitals. Several others remained trapped in the wreckage.
This ball of steel would be, I'd liken it to an onion. As you stripped away pieces of metal, other pieces moved in another direction, and that's what made the whole extrication so difficult.
The force of the impact caused the 2 trains to balloon to the full diameter of the tunnel. The expansion of the cars sealed off the tunnel's airflow and ventilation. Over 200 rescuers faced unbearable conditions. In temperatures that exceeded 100 degrees Fahrenheit, they were forced to crawl beneath the subway cars to reach the trapped passengers.
I'd liken it to putting 12 to 20 rescue workers inside an 8x8 sauna and asking them to work for 8.5 hours in there with all their gear on. It was that tough for those people.
Using power saws, rescue crews cut away the jagged metal of the crushed cars. Shearing the metal apart was a Herculean effort requiring surgeon-like delicacy. Cutting open one side of the train generated movement, jeopardizing the rescue of passengers trapped in other areas. As the rescue effort proceeded into the early hours of the morning, the accident claimed its first 2 victims. But one woman trapped in the crushed debris was still alive.
Right now, there's one patient on the other side of the steam. Still trapped, but who's stable. There's one critical patient trapped, and the child is just
Rescue crews worked feverishly in the cramped conditions to free her. After several hours, the critically injured woman was finally pulled free. Despite the heroic efforts of rescuers, the woman's injuries were too severe and she died on the scene.
The one thing that probably stays with a lot of the guys is the one victim that we helped out in the tunnel, and she didn't survive. She was conscious for a fair bit of the time. I meant to learn later on that she didn't survive. That's a tough thing to have to deal with.
A total of 3 people died in the crash. 30 passengers and 3 train crew members were injured. The cause of the accident? A series of errors leading to a system-wide breakdown.
No single person was responsible for this. It was a set of system-wide, built-in, latent errors which happened to coincide on this particular occasion in a collision.
The TTC investigation determined the probable causes of the accident. Traveling at 35 miles an hour, the driver of Run 35 sped through 3 red signals before colliding with Run 34. But the accident wasn't caused by human error alone. A mechanical malfunction also occurred. When Run 35 went through the red signal lights, a trip arm safety device should have triggered the train's emergency braking system. When a signal light is red, the train stop arm is in the up position on the track. When the signal is green, the arm is down. If a train goes through a red signal, the stop arm trips a lever under the train, which should apply the brakes. In the case of Run 35, the trip arm failed to trigger the braking device.
For the TTC, it was the single most gut-wrenching moment in the history of the Commission. It was something this organization took very seriously. In fact, I think it's fair to say that it was the most tragic incident, and it's the incident that, above all else, in my experience, that's caused the TTC to examine itself and its role and its performance from top to bottom.
As a result of the accident, the TTC implemented several new policies, including new training programs for drivers, strict disciplinary actions for signal violations, and a more thorough examination and replacement of aging equipment. While runaway subway and other passenger trains command attention because of the potential loss of life, they're not the only source of danger on the rails.
How do we ensure situations like this do not occur at BART?
The answer is properly using configuration management. As stated earlier, change management or configuration management is a process to ensure that all documentation that describes a system and its various components is current and reflects the actual functional and physical characteristics of the system throughout its life cycle.
The foundation of a management of change process is an effective configuration management control process, including
the authority to make configuration changes,
process for making changes,
assurances necessary for formally notifying all involved departments.
Configuration management controls include the following:
Configuration Control Review Board, CCRB.
Document control.
Materials control.
Configuration management procedures.
Configuration audits.